You are currently sitting on a rock flying through space at 670,000 mph. That rock orbits a 1 million times larger nuclear furnace. That furnace is one of 400 billion stars moving through a massive galaxy. The light itself. It takes 100,000 years to cross it. But here is what will blow your mind. Our entire galaxy, with all of its billions of worlds and numerous civilizations that may exist, is nothing more than a single grain of sand in an ocean of 2 trillion grains. If you love journeys that transform your perspective on reality, click the like button and subscribe. Prepare yourselves. We begin. Imagine yourself standing in the heart of New York City at midnight. The lights reach eternally in all directions. Buildings fade into darkness near the horizon. Consider that cityscape expanding not only to the next state, but throughout the continental United States. Then stretch it from the Pacific Ocean to Asia. Keep expanding it around the entire planet. Then double the distance by 6 billion. You've just visualized the width of our galaxy. Scientists proved through careful measurements that the Milky Way is 100,000 light-years long from end to edge. 1 light-year is 6 trillion miles. This indicates our galaxy is 600,000 trillion miles across. Writing that number would necessitate a line of zeros spanning from your house to the nearest grocery shop. But here comes the first jolt to human intuition. Despite this mind-boggling scale, our galaxy is only the first rung on a cosmic ladder. That approaches infinity. Our brains are unable to process every single point of light. The stars you see flashing in the night sky are from our galaxy. The fuzzy strip of stars cutting across the dark skies provides an edge-on picture of our spiral arms. We dwell within this cosmic city, like a single cell within a large body. From our position, we are around 26,000 light-years from the galactic center. We can see star formation areas where new suns ignite. Every year, we see star nurseries in which gravity shapes gas clouds into glowing spheres. Ancient red giants die in dramatic explosions, seeding space with heavy elements. All of this cosmic drama occurs within our local galaxy theater. However, what makes this scale genuinely alarming is not its size, but what it signifies. Our galaxy is simply one unit in a huge and incomprehensible hierarchy of systems. Each level of cosmic order dwarfs the previous one due to forces that make human experience worthless. Standing on Earth and pondering galactic distances is like an ant attempting to grasp the size of North America. The ant perceives that something immense exists beyond its immediate surroundings. However, it lacks the cognitive framework required to understand continental scales. When dealing with cosmic distances, humans encounter the same limitations. Our developed brains, suited for hunting on African plains, struggle with scales larger than our immediate environment. This cognitive barrier is our first indication that the universe functions at levels far beyond human comprehension. Each cosmic structure we find forces us to shed our earthbound perceptions and accept scales that resemble mathematical abstractions rather than physical reality. The ancient Greeks believed that the stars were holes in a heavenly sphere that surrounded the Earth. Modern astronomy suggests that our galaxy alone has mysteries that would have beyond their wildest expectations. Every telescope that stares deeper into space reveals fresh levels of cosmic organization stretching into horizons we can scarcely see. Yet in comparison to what follows, our galaxy appears to be a single room in a cosmic mansion with countless floors spreading into infinity. Light travels faster than anything else in the universe. Nothing can outrun a photon flying across space at 670 million miles per hour. Light travels around the Earth 7 times in a single second. This cosmic speed limit reflects the fastest means to travel across distances in our reality. However, even light, the ultimate sprinter of physics, takes 100,000 years to get from one extreme of our galaxy to another. Consider what this entails from the human standpoint. Tonight, light left distant stars in our galaxy and began its trek. When early humans learned to produce fire, photons from the far side of the Milky Way began to travel to Earth before written language was invented. These ancient light particles include information on celestial events that occurred while our ancestors were still discovering agriculture. Astronomers utilize this light journey time as a cosmic measuring stick when studying distant galaxy regions. They perceive them as they were thousands of years ago. The galaxy we saw tonight is actually a patchwork of various historical eras. Nearby stars reveal recent happenings. The distant stellar neighborhoods reveal old history. We never see our galaxy as it is right now, but rather as a time-averaged composite spanning millennia. This temporal displacement results in one of astronomy's most unusual proven facts. Every snapshot of our galaxy depicts numerous time periods at once. The light from distinct cosmic areas left their sources at different historical times. Looking at the Milky Way implies looking back in time across a period longer than human civilization. However, when we incorporate galactic rotation, the voyage duration becomes much more mind-bending. The entire galaxy revolves like a cosmic pinwheel. The solar system rounds the galactic center once every 200 million years as light travels throughout our galaxy, completing approximately half a rotation. The galaxy literally changes shape as light moves between its sections. Even more worrisome is the implication for cosmic communication. Any attempt to transmit signals across our galaxy encounters this fundamental obstacle. Radio waves and laser beams travel at light speed. Therefore, galactic communication necessitates patience measured in geological time. If an alien civilization on the other side of our galaxy sent us a message today, our great-great-grandchildren would have to wait for it to be delivered to them. This is a communication barrier. This implies that our galaxy can never function as a cohesive system. Different regions operate separately, separated by the fundamental speed limit for information transfer. What appears to be a single cosmic structure is actually made up of numerous independent zones, each forming without knowledge of distant galactic neighbors. The old photons reaching us tonight contain messages from a galaxy past that we can see but never revisit. Every star we observe reveals information about conditions that existed before our species learned to look up at the night sky. However, this galactic communication barrier illustrates only the smallest scale problem we confront when attempting to fathom cosmic distances. Simply step outdoors on a clear night and locate the brightest star in the sky. The dazzling point of light is Sirius. It burns 25 times brighter than our Sunday. It seems so bright that ancient civilizations built their calendars around its movements. It appears close enough to reach with a reasonably tall ladder. The confirmed fact shatters this illusion totally. It is 8 and 6-10ths light-years away from Earth. This distance equals 51 trillion miles. If you could drive a car at highway speeds to the nearest brilliant star, the voyage would take 300 million years. You would need to maintain a constant speed of 65 miles per hour, since before complex life originated on Earth. Yet Sirius is almost next door when compared to usual galactic distances. Most stars in our galaxy are separated by enormous gaps that surpass human comprehension. The average distance between adjacent stars is 4 light-years. In cosmic terms, this is an almost perfect vacuum punctured by a few tiny islands of matter. To visualize this void, consider decreasing our solar system until the Sun is the size of a basketball. At this scale, Earth is equivalent to a grain of sand orbiting 26 feet away. The nearest star would be another basketball in a different city, like Denver. Suppose you started in New York. Everything between these basketballs is essentially empty space. This emptiness has far-reaching ramifications for interstellar travel between stars. Even at the speed of light, travels to nearby stars take years. Conventional spacecraft traveling at feasible speeds would take tens of thousands of years to reach their closest star neighbors. The vast portion of our galaxy is permanently unavailable to human exploration. The space between stars also explains why alien contact appears so unlikely, despite the vast number of viable worlds. If alien civilizations exist on planets orbiting distant stars, they confront the same fundamental limitations to space and time that keep us apart. The universe conspires to keep sentient species divided by gulfs that are too large for meaningful interaction. Scientists estimate that our galaxy contains approximately 400 billion stars. However, these uncountable suns are so unevenly distributed over galactic space that each one exists. The night sky generates an optical illusion when seen in complete darkness, making stars appear clustered together when they truly live in a world of cosmic solitude. This stellar isolation continues throughout our whole galactic neighborhood, including the Milky Way's dense center regions, where stars cluster closer together than in our outer spiral arcs, maintain large vacant spaces between each sun. The galaxy that appears so rich and inhabited in telescope photographs is actually primarily vacuum. Observing the empty spaces between stars gives us our first glimpse into the fundamental structure of cosmic architecture. Matter represents uncommon exceptions in an otherwise empty universe. We live in a little oasis of substance, floating in an ocean of nothingness. However, this cosmic void appears positively filled in comparison to the spaces that separate entire galaxies. Consider counting each star in our galaxy. Begin with the Sun and work your way out through the spiral arms. Count each red dwarf, each blue behemoth, and consider each binary system spinning through space. Maintain a constant rate of 1 star per second without pausing to sleep or eat. You'd finish counting. After 600 years of confirmed observations by space observatories, our galaxy is estimated to contain between 100 billion stars and 400 billion stars. The actual quantity is unknown since dust clouds obscure our vision of remote galactic areas. The dark nebula hides star populations that can only be detected by infrared light. But even a conservative estimate of 100 billion stars is beyond human comprehension. Every second, one of these star furnaces generates nuclear fusion energy. The Sun turns 4 million tons of stuff into pure energy. Multiply this output by hundreds of billions of comparable reactions occurring at the same time around our galaxy. The Milky Way's overall energy production exceeds the power consumption of human civilization for reasons that require scientific notation to convey. However, this enormous, brilliant population brings an uncomfortable truth. Despite having enough suns to power quadrillions of civilizations, our galaxy is a mere fraction of cosmic existence. Astronomers describe the Milky Way as a medium-sized spiral galaxy. Larger galaxies contain more than 1 trillion stars, while tiny dwarf galaxies have only a few billion stellar furnaces. The probability mathematics surrounding galactic star counts indicates astonishing potential for planetary systems. If even 1% of galactic stars contain Earth-like planets, our galaxy has billions of potentially habitable planets. Some of these worlds may have civilizations that are much older and more advanced than human society. Others might include life forms that are so strange. We lack the vocabulary to articulate these numbers, but what genuinely disturbs us is their cosmic insignificance. Every star we've ever seen, every planet we might discover, and every extraterrestrial civilization that could live inside our galactic borders accounts for less than 1% of the stuff in the observable universe. Our galaxy, with its myriad worlds, is like a single grain of sand on an endless beach. This shift in perspective calls into question human-centered assumptions about our cosmic importance. The old assumption that Earth was at the center of creation appears antiquated in comparison to recent discoveries regarding cosmic scales. We live on one planet orbiting one star out of hundreds of billions in a galaxy with trillions of comparable structures. Our galaxy's 400 billion stars produce energy that dwarf terrestrial events. Their combined light output produces the dazzling band we see stretching over the black skies. Their gravitational interactions create the spiral arms where new stars continue to build their life cycles, seeding space with heavy elements required for rocky planet formation and biological evolution. All of this cosmic splendor takes place within what amounts to our immediate galactic neighborhood. The next level of cosmic order makes our entire celestial city appear to be a single house on an endless street. Look at the constellation Andromeda. On any October night, the little smear of light appears indistinguishable among the stars. Ancient astronomers classified it as a nebula, considering it belonged to our cosmic neighborhood. Modern telescopes reveal a truth that should be both terrifying and inspiring. You're staring at another galaxy with over 1 trillion stars. The Andromeda Galaxy is 220,000 light-years across, more than double the diameter of our Milky Way. This galactic monster has enough stellar furnaces to outnumber our own star count by a ratio of 3 or 4, if our galaxy were New York City. Andromeda covers the entire eastern coast of the United States, but confirmed measurements reveal something even more astonishing. Andromeda is speeding toward us at 250,000 kilometers per hour. This cosmic collision course will result in the most stunning event our solar system has ever seen. Computer simulations predict that after 4.5 billion years, these two galactic titans will converge. The collision will change both spiral formations during a gravitational dance that will last billions of years into a single elliptical galaxy, which astronomers have previously called Eta. During this union, our solar system is likely to survive intact. Stellar collisions are highly improbable, even during galactic impacts, due to the immense distances between individual stars. Instead, gravitational forces will propel our Sun and planets into new orbits. Around the United Galactic Center, Earth may wind up in the outer parts of the merged galaxy, staring at unknown constellations. But what makes Andromeda genuinely mind-bending is not its magnitude or the impending collision, but what it represents about cosmic distances. The lights you see today from Andromeda started their journey 2.5 million years ago, when photons began to move toward Earth. Early human predecessors were still learning to use stone tools. The cosmos that you see existed before contemporary people arose. Because of this temporal displacement, we will never be able to witness Andromeda as it currently exists. We see its ancient past, preserved in light, that has traveled through the cosmic emptiness for millions of years. The galaxy approaching us right now may appear radically different from what we see through telescopes. Even more alarming is Andromeda's revelation concerning cosmic scales. Despite being our nearest major galactic neighbor, it is really far away. That light takes millions of years to bridge the divide. This distance is the shortest meaningful step beyond our immediate galactic environment. Between our galaxy and Andromeda is a gap filled with nearly nothing but dark matter and dispersed gas clouds. This intergalactic space contains temperatures close to absolute zero and densities lower than the best vacuum chambers we can build. However, this seemingly barren gulf is teeming with invisible powers that govern galactic motions throughout cosmic time. Our galaxy's impending merger with Andromeda will result in visible fireworks from distant galactic neighborhoods. However, even this cosmic show is simply a local occurrence in a far wider gravitational theater. Our galaxy is not alone in cosmic space, it is part of a gravitational family known as the local group. There are almost 50 distinct galaxies entangled in an endless cosmic dance. This galactic neighborhood covers around 10 million light-years and contains enough combined mass to bend space and time over huge distances. Based on confirmed observations, the majority of galaxies in our local group are dwarf systems with only a few billion stars. These cosmic midgets orbit the two main spiral galaxies. Our Milky Way and the coming Andromeda are like planets orbiting a binary star system. These smaller galaxies have intricate orbital patterns controlled by the gravitational interaction of the two larger group members. The Magellan Clouds, which are visible to naked eye observers in the southern hemisphere, are the most notable dwarf companions. These irregular galaxies orbit the Milky Way at a distance of 100 light-years, 60 Cirrus-Indo and 200 Cirrus-Inno light-years, respectively. Their proximity makes them ideal for researching galactic interactions in real time. Scientists have revealed that our galaxy actively cannibalizes its smaller neighbors. The Milky Way's tidal forces and massive gravitational field take stars and gas from the Magellan Clouds, injecting material into our galactic disk. This cosmic feeding process has been ongoing for billions of years, with our galaxy expanding by absorbing adjacent dwarf systems. However, Galactic predation shows something important about cosmic evolution. Galaxies do not exist as solitary islands floating in empty space. They live in gravitational communities, where continual interactions influence their structure and evolution. The serene look of night sky galaxies conceals violent activities occurring across cosmic timescales. The local group moves through space as a unified unit. Our entire galactic neighborhood is traveling at approximately 400 miles per second toward the Virgo cluster. This motion transports our local collection of galaxies over vast distances that dwarf individual galaxy sizes. We are passengers on a cosmic spaceship sailing through intergalactic space toward gravitational destinations we can scarcely detect as more amazing. The galaxies in our local group are connected by dark matter halos that stretch far beyond their visible borders. These unseen gravitational structures hold 10 times the mass of all visible stars and gas. Dark matter acts as a gravitational glue, holding galaxy clusters together, despite the expansion of space itself. The orbital dynamics of our local group adhere to precise mathematical principles that regulate motion on cosmic scales. Each galaxy follows elliptical trajectories through space, periodically approaching and withdrawing from its neighbors in billion-year cycles. These gravitational interactions cause star formation, change galaxy structures, and redistribute mass over long distances. Understanding our celestial surroundings necessitates thinking on timescales that beyond human experience. The current configuration of the local group is only one point in a cosmic development that spans tens of billions of years. Galaxies separate and re-merge in patterns too slow for human perception, but recorded in the motions we see today. This local gravitational dance is only the tiniest organizational unit of an ever-expanding cosmic hierarchy. Galaxy clusters are the most enormous gravitationally bound structures in the cosmos. These cosmic metropolis are made up of thousands of separate galaxies bonded together by tremendous forces that bend space and time across millions of light years. The nearest big cluster, Virgo, comprises around 1,300 galaxies and is 54 million light-years from our local group. According to confirmed observations, galaxy clusters should not exist based on the visible stuff observed. The combined gravitational pull of all the stars and gas in cluster galaxies cannot account for the enormous forces required to hold these structures together. Galaxies within clusters travel at rates reaching 3 million miles per hour. Such velocities would have dispersed cluster members throughout cosmic space billions of years ago. The solution to this puzzle involved discovering that the majority of the cluster mass is absolutely undetectable. Dark matter exceeds visible stars and gas by a 10-to-1 ratio across galaxy clusters. This unknown material is only revealed through gravitational effects on light and matter, creating a cosmic scaffolding that can be mapped but not directly observed. Scientists utilize gravitational lensing to analyze the distribution of dark matter in galaxy clusters. Massive clusters bend space so severely that they behave as cosmic magnifying glasses, distorting the appearance of surrounding galaxies. The amount of distortion indicates how much invisible mass clusters contain. These findings confirm that dark matter dominates cluster structure. Despite being undetectable by any human-made device, the most stunning example of dark matter evidence comes from the Bullet Cluster, when two galaxy clusters collided at speeds surpassing 10 million miles per hour. During this cosmic collision, visible gas clouds interacted and slowed, yet dark matter components went through each other unaffected. Gravitational lensing maps show dark and visible matter separated by millions of light years, offering direct evidence that invisible mass exists independently of stars and gas. Galaxy clusters are also used as cosmic laboratories to investigate extreme physics. The heated gas between cluster galaxies reaches temperatures of 100 million degrees, hot enough to remove electrons from atoms, create plasma that lights at X-ray wavelengths. This superheated material has more mass than all of the cluster galaxies together, but optical telescopes cannot see it. The space between cluster galaxies is filled with high-energy particles pushed to near-light speed by magnetic fields that span millions of light-years. These cosmic ray particles produce radio emissions that can be detected by sophisticated telescopes, showing magnetic patterns that connect distant galaxies inside clusters. The function that galaxy clusters play in cosmic evolution, however, is genuinely mind-bending. Clusters reflect the gravitational collapse in our cosmos. Shortly after the Big Bang, dark matter began clumping. These galactic groups eventually combined to form gravitational wells where galaxies developed over cosmic time, resulting in increasingly large clusters. El Godo, the biggest known galaxy cluster, with the mass of 3 quadrillion suns and a span of 15 million light-years. This cosmic behemoth is 7 billion light-years away, meaning we see it as it existed when our solar system was still emerging. Galaxy clusters are nodes in a much greater cosmic structure that resembles a three-dimensional spiderweb. Superclusters are the largest confirmed gravitational formations in our universe. These cosmic creations span across such enormous distances that light takes hundreds of millions of years to go through them. Our local group is part of the Lanya Key supercluster, a gravitational collection that spans 500 million light-years and contains more than 100,000 galaxies. The discovery of superclusters transformed our view of cosmic order. Instead of being randomly spread throughout space, galaxies form huge networks connected by filaments of dark matter and gas. These cosmic highways transport materials over vast distances that dwarf individual galaxy clusters, resulting in a hierarchical structure that stretches to the biggest observable scale. Scientists mapped our local supercluster by studying the odd movements of thousands of galaxies. Despite cosmic expansion, which pushes distant galaxies apart, gravity causes closer galaxies to gravitate to denser regions. Astronomers discovered that our Milky Way and millions of other galaxies are all convergent on a gigantic gravitational attractor by monitoring these gravitational flows. This attractor, known as the Great Attractor, includes the combined mass of tens of thousands of galaxies in a region covered by dust clouds on our galactic plane. The gravitational pull of this cosmic monster affects galaxy movements over hundreds of millions of light-years, causing currents in the cosmic web that transport entire galaxy clusters to areas of increasing density. But the enormous attractor is simply a small part of a much greater system. Recent observations show that Leia Cares. It is part of a massive complex of superclusters spanning more than 1 billion light-years. The Pisces-Theta supercluster complex may be the largest coherent structure in the observable cosmos. The implications of supercluster organization raise questions about our knowledge of cosmic evolution. These massive structures were produced through gravitational processes that took billions of years. Dark matter is what creates the patterns we see today. When the universe was less than 1% of its current age, it began to coalesce, eventually becoming the scaffolding upon which visible matter ordered itself. Cluster borders are still difficult to define exactly since they merge into adjacent structures. Unlike galaxy clusters, which are obviously bound by gravity, superclusters are looser affiliations that may be dispersed as a result of cosmic expansion. Some places within superclusters continue to collapse under their own gravity, while other places are being stretched apart by dark energy. Superclusters resemble biological formations rather than geometric things. Lank resembles a large sheet with tendrils stretching in all directions, comparable to neural networks in the human brain. This likeness may not be coincidence, as both systems are organized using processes. This results in branching hierarchical systems. Observing supercluster structure necessitates telescopes capable of mapping millions of galaxies over long distances. By calculating accurate distances to over 1 million galaxies, the Sloan Digital Sky Survey was able to construct three-dimensional maps that revealed supercluster organization. These studies reveal that superclusters combine to generate even larger structures resembling cosmic scaffolding. The cosmic web that results from supercluster mapping resembles soap bubbles floating in space, with galaxies concentrated along the bubble edges and massive gaps occupying the bubble interior. This soap bubble architecture extends throughout the observable cosmos. Walk back far enough, and a magnificent pattern appears. Galaxies do not spread randomly across space, but rather form a massive three-dimensional network that resembles soap foam floating in cosmic darkness. The cosmic web is the biggest size organization of stuff in our universe. Computer simulations show that this web-like design originated spontaneously through gravitational processes. Dark matter began clumping together shortly after the Big Bang, when the universe was only a few 100,000 years old, forming gravitational seeds that eventually developed into the cosmic framework we see today. The cosmic web is made up of 4 unique components that work together across billions of light years to form dense nodes, mark the intersections where galaxy clusters produce filaments that run between nodes like cosmic highways, channeling matter across vast distances. Walls form sheet-like structures where filaments intersect. These structures resemble cosmic gaps, comprising essentially nothing but empty space. Scientists have mapped this cosmic architecture by viewing millions of galaxies and determining their three-dimensional positions in space. The resulting studies show that galaxies trace the edges of huge bubbles, with emptiness regions occupying the bubble interiors. This foam-like structure exists throughout the observable cosmos. With astonishing regularity, the magnitude of cosmic web components defies human intuition. Individual filaments span hundreds of millions of light years while maintaining diameters of only 20 million light years. When viewed on a vast scale, these cosmic threads appear impossibly thin, but they contain enough matter to fuel billions of galaxies' stuff flowing along filaments like water. Galaxy clusters arise where several filaments overlap, resulting in gravitational traffic jams that confine matter for billions of years. These cosmic crossroads are the busiest locations in the universe, where galaxy interactions cause star formation and supermassive black hole growth. The largest huge clusters represent the places of the cosmic web. It reaches its maximum density. The dynamic aspect of the cosmic web, however, is what truly sets it apart. This structure is always changing. As the cosmos expands, dark energy accelerates the separation of distant places. Filaments that currently link distant superclusters will eventually snap. As space stretches beyond the reach of gravitational forces, the gas threading between cosmic web filaments is mainly invisible to optical telescopes, but it glows dimly at ultraviolet and X-ray wavelengths. This intergalactic medium has more mass than all the stars in the universe combined, but it is so thin that cubic meters of it contain only a few atoms. Recent observations. We discovered the warm, hot intergalactic medium predicted to fill cosmic web filaments. This substance achieves temperatures of millions of degrees while maintaining densities just above the cosmic vacuum. Finding this elusive component needed specialized X-ray telescopes capable of detecting extremely faint emissions from heated gas. The cosmic web goes beyond our existing observational capabilities. This suggests that the structures we can map only represent a small portion of the universal organization concealed within this web. They challenge our notion of space in the same way as cosmic voids do. Imagine a 300 million light-year wide disk of space that contains absolutely nothing. There are no galaxies shining in this vast wilderness. There are no stars to brighten the gloom. There are no planets orbiting through its emptiness. This empty zone, known as the cosmic void, is one of the most perplexing locations in our world. The Boyer's void, found in 1977, measures 330 million light-years in diameter and contains fewer than 60 known galaxies. If our small group existed within this cosmic bubble, the nearest large galaxy would be so far away that it would show as a faint smudge in our most powerful telescopes. According to confirmed observations, cosmic voids account for around 80% of the universe's volume. These massive empty spaces that separate the cosmic web filaments, where galaxies cluster together, comprise less than 15% of the average matter density. Located elsewhere in the universe, scientists initially struggled to understand how such empty spaces could occur. Early theories proposed that voids were generated by explosive events that removed stuff from vast expanses of space. Modern study shows that voids are natural results. As matter clumped together along filaments and walls, it drained away from vacuum regions during cosmic web development. The vacuum of cosmic voids creates conditions that are unlike anything else in the observable cosmos. Temperatures inside voids hover just a few degrees higher. Absolute zero. Individual hydrogen atoms can be separated by miles rather than tiny dimensions due to low densities. These circumstances approach the ideal vacuum that physicists can only make in specially designed laboratory chambers. However, voids are not fully empty. They include invisible dark matter, which forms the gravitational framework that connects them to the surrounding structures. Computer models reveal that vacuum regions contain dark matter filaments, which are too tenuous to gravitationally confine regular matter. These unseen strands form a web within the web, extending cosmic order into the seemingly empty space. Galaxies that live within voids evolve differently than their counterparts in denser locations. Void galaxies are smaller, bluer, and have a higher rate of star formation than ordinary galaxies. These unusual galaxies are isolated within voids, which protects them from gravitational interactions that would disturb their star formation processes. The giant vacuum, also known as the Keynes-Fanatic supervacuum, spans 1.8 billion light-years and contains very little matter. That if our Milky Way was at the center, we would not have discovered additional galaxies until the 1960s. Except for our local galactic neighbors, the night sky would be nearly pitch black. Cosmic voids also have an effect on cosmic microwave background radiation, which is left over from the Big Bang. Photons moving through void regions encounter somewhat different gravitational forces than those passing through denser areas. There are modest temperature differences. Provide another method for mapping void locations across cosmic distances. The expansion of space preferentially impacts void regions, leading them to become larger over time, while matter continues to flow towards nearby structures. Even these massive empty spaces appear little in comparison to the greatest solid structures discovered by astronomers. The observable universe's greatest solid structures span such huge distances. They push the fundamental boundaries of what cosmic physics should allow. These massive walls and sheets of galaxies stretch billions of light-years, despite having thicknesses of only 20 million light-years, resulting in cosmic architecture that resembles impossibly thin membranes floating through space. Astronomers discovered the first galaxy wall, known as the Coma Wall, which is 500 million light-years long and only 16 million light-years thick. This cosmic structure is made up of thousands of galaxies stacked in a thin sheet that appears edge-on as a barely discernible line. If viewed from the side, the wall is 300 million light-years away from our local group. Although it is a major feature in our cosmic neighborhood, confirmed observations have revealed even larger structures that challenge theoretical expectations. The Sloan Great Wall is one of the universe's largest known structures, measuring 1.3 billion light-years wide. This cosmic barrier is made up of hundreds of thousands of galaxies that have been structured into a coherent pattern. That covers around 1% of the observable universe. Diameter. Even more amazing is the Hercules Corona Borealis Great Wall, discovered by monitoring gamma-ray bursts from distant galaxies. This structure is 10 billion light-years across. It is so enormous that light takes more than 1/10 of the universe's age to get from one end to the other. The emergence of such massive structures calls into question theoretical notions of how cosmic organizations should grow. Galactic walls occur when cosmic web filaments intersect over huge distances. Computer simulations demonstrate that dark matter naturally forms sheet-like structures. When gravitational forces pull matter together from various directions at the same time, normal matter follows the dark matter filaments, resulting in the observed galaxy concentrations. The thinness of cosmic barriers generates gravitational factors that influence galaxy evolution at vast distances. Galaxies within walls undergo stronger tidal forces, which can cause star formation bursts and the separation of matter from smaller adjacent systems. The gravitational environment within walls changes greatly from that in cosmic gaps or dense cluster cores. Scientists utilize cosmic walls as labs to investigate large-scale structure creation. The precise arrangement of galaxies within walls reveals information about the early conditions that prevailed soon after the Big Bang. Comparing observable wall formations to computer simulations allows researchers to evaluate theories about dark matter features and cosmic evolution. However, what genuinely amazes me about these barriers is their significance in universal organizing. Despite their massive size, cosmic barriers are intermediate-scale structures between superclusters and the biggest detectable patterns in galaxy distribution. They are components of considerably bigger organizational structures. That extends to the limits of observational capability. The discovery of cosmic walls also demonstrates the dynamic character of large-scale structures. These gigantic features continue to evolve as the universe expands. The universe. Walls that appear solid today will someday fracture as dark energy outweighs gravitational forces. Some cosmic walls, which hold their components together, may stretch beyond our current observational horizon. We are still unable to detect this possibility while connecting structures. Hints for organizing structures that span the entire observable cosmos. Point the most powerful telescope ever built at a little piece of seemingly empty sky. Keep the camera open for days, gathering any photons that come from that cosmic direction. The final image will disclose something that should radically alter your perspective on existence. Thousands of galaxies can be found in that tiny region, which is no bigger than a grain of sand when held at arm length. The Hubble Ultra Deep Field was made by merging 800 individual photos with 11 days of total exposure time, revealing approximately 10,000 galaxies in a region of sky covering about 1/13 millionth of the celestial sphere. Each galaxy in this cosmic census has billions of stars, many of which are likely to house planetary systems capable of supporting life. Astronomers can use confirmed deep field data to compute the total galaxy population in our observable universe. The most recent estimations are based on data from the Hubble and James Webb Space Telescopes. Assume that 2 trillion galaxies inhabit the cosmic volume that we can currently detect. 2 trillion is a figure that defies human comprehension. If you could observe one galaxy each second without pausing, it would take 63,000,000 years to write them all down entirely. This figure requires 13 zeros and 2 million galaxies spread over observable space. Each of these galactic islands has its own stellar population. Conservative estimates indicate that the average galaxy has 100 billion stars. Multiplying galaxy counts by stellar populations results in a cosmic census that exceeds 10 to the 24th power individual stars. This figure outnumbers the amount of grains of sand on every beach on Earth. But what makes this galactic abundance so disturbing is how it rebalances significance in the cosmic hierarchy. Our entire local group of around 50 galaxies accounts for less than 1/50 billionth of the total galactic population, which includes the Milky Way and its 400 billion stars. Ranks as completely typical of the 2 trillion cosmic neighbors who share our cosmos. Recent findings imply that galaxy counts may underestimate universal populations. Improved detecting methods continue to discover weak dwarf galaxies. Previous scans missed these small galaxy systems with only millions of stars. Each may outnumber larger spiral galaxies. Deep field investigations reveal galaxies at various stages of cosmic evolution, as they existed billions of years ago when the universe was young and star formation rates were higher than now. These ancient systems had distinct structures and compositions than neighboring present galaxies, revealing insights into cosmic history and the dispersal of galaxies throughout space. Galaxy numbers follow the cosmic web pattern, extending to the largest visible scales while remaining fairly constant in all directions. Astronomers are looking for evidence that global structure appears uniform when viewed from cosmic distances. This consistency indicates that our observable volume is a representative sampling of universal contents. Nonetheless, every galaxy survey delves farther into space, reveals more cosmic neighbors that were previously concealed beyond detection limitations. Every increase in telescope sensitivity adds billions of galaxies to the cosmic census. The 2 trillion galaxies we can now observe may only be a small percentage of the entire galaxy population. Walk along any ocean or shoreline and collect a handful of sand. Count the granules between your fingertips. A usual handful contains around 10,000 small bits of rock and shell, with each grain representing millions of years of erosion and weathering. Now, broaden your count to include every beach on Earth. Include the Caribbean islands, the Mediterranean coast, the Pacific atolls, and the Arctic shores. Count every grain of sand on every beach that surrounds each continent and island on the Earth. Scientists believe that the world's beaches contain around 7 quintillion grains of sand inscribed with zeros. This number contains 20 digits, 7 million particles. This astronomical count of earthly sand grains is insignificant in contrast to cosmic stellar populations. Confirmed observations show that the observable cosmos includes more stars than grains of sand on Earth. The 2 trillion galaxies we can discover contain enough star furnaces to outnumber our planet's sand count by thousands of times. Every time you pick up a handful of beach sand, keep in mind that cosmic space holds thousands of stars for every grain between your fingers. However, when we include global populations, the comparison becomes even more startling. According to recent exoplanet studies, the majority of stars have at least one planet. With many systems having numerous worlds, conservative estimates suggest that the observable universe has more planets than sand grains on Earth, multiplied by the total number of atoms. Each of these uncountable worlds is a distinct experiment in planetary evolution. Rocky planets orbit in regions where liquid water may occur. Gas giants dominate the outer planetary zones. Ice worlds harbor subsurface oceans, whereas desert planets broil under high solar radiation. The variety of planetary ecosystems much exceeds anything science fiction has conceived. The probability calculations around these figures reveal mind-boggling implications for life in the universe. Even if life emerges on only one planet out of a million eligible worlds, the cosmos should be brimming with biological activity. Some civilizations may have evolved billions of years before Earth began. Others may possess technologies that make human achievements appear primitive. However, the huge distances between star systems cause isolation, preventing most planets from ever conversing with their cosmic neighbors. The speed of light barrier assures that civilizations separated by thousands of light years will never make meaningful communication. Each inhabited world grows in cosmic solitude. They are unaware of the myriad other intelligence tests taking place throughout the universe. This seclusion explains why the night sky appears so peaceful. Despite the large number of potential cosmic neighbors, radio communications from alien civilizations would take centuries or millennia to traverse the distance between star systems. By the time signals reach, the civilizations that sent them may have developed beyond recognition or disappeared completely. The star census also gives remarkable insights into cosmic perspective. Every human who has ever lived lives on one planet, orbiting one star, surrounded by more stellar furnaces than there are sand grains on Earth. However, this amazing stellar abundance is only the beginning of cosmic proportions that exceed even these mind-boggling figures. The universe you see tonight contains boundaries, not physical walls, that indicate the end of space. However, basic limitations are imposed by the speed of light and the age of cosmic time. These bounds define what astronomers call the observable universe, which is a sphere of space that contains everything we could theoretically detect using any technology that humanity may ever invent. Confirmed measurements show that this visible sphere is 93 billion light-years in diameter. This distance indicates the greatest expanse of space from which light has had time to reach Earth since the universe began. Beyond this cosmic horizon lies a realm permanently hidden from human gaze. To calculate this cosmic barrier, you must comprehend both light travel time and cosmic expansion. Light from the most distant, detectable objects began to travel 13.8 billion years ago, when the cosmos was only 380,000 years old. However, cosmic expansion increased the distance between the source and destination objects that emitted light 13.8 billion years ago. As a result of the cosmic stretching, We now live 46.5 billion light-years away. Light from faraway galaxies that were quite nearby arrives on Earth, after the same galaxies have been transported to even greater distances by expanding space. This results in one of the most perplexing truths about cosmic observation. The most distant galaxies we can observe appear to have existed when the cosmos was young and tiny. However, those galaxies still reside far beyond our observational horizon. Evolved into forms that we can never see directly, the cosmic microwave background radiation, the afterglow of the formation of atoms, and the transformation of space into a light-transparent medium marks the end of the visible cosmos. This radiation gives a snapshot of the cosmos at less than 1% of its present age. The viewable horizon, however, is truly mind-bending due of its personal nature. Every observer in the universe has their own distinct observable sphere centered on their position. Alien scientists in faraway galaxies view cosmic volumes that overlap by hours in certain areas while extending into space that we will never see. Every day, the observable cosmos expands as light from progressively distant locations first reaches Earth. Over cosmic time, our visibility grows by 1 light second in every direction. This progressive extension of the observational range shows new galaxies that emerge from beyond the cosmic horizon. However, this increased visibility cannot last indefinitely. Cosmic expansion will eventually outpace light travel, forcing distant galaxies to pass forever beyond our observational reach. The observable universe will begin to shrink as expansion transports cosmic neighbors beyond the cosmic horizon, never to be seen again. Current observations indicate that we live in a golden age of cosmic visibility. The observable universe now has more galaxies than at any other moment in cosmic history. However, fewer will be visible in the long future when growth isolates us from increasingly distant neighbors. This cosmic border raises fundamental issues regarding the nature of space beyond our observable boundaries. The cosmos we cannot see may be substantially greater than the cosmic volume visible to human eyes. Space itself travels faster than light. This comment appears to go against Einstein's cosmic speed limit. However, verifiable measurements show that the fabric of space-time grows at rates that dwarf the speed of photons rushing through the cosmic abyss. Einstein's relativity forbids matter and energy from traveling faster than light across space, while space has no such restriction. The universe can stretch its own fabric in any direction without breaking physical principles. During cosmic inflation, space expanded extremely rapidly. Regions separated by subatomic distances expanded to cosmic scales in less than a second. This contrast between velocity through space and expansion of space has far-reaching implications for cosmic observation galaxies on the outskirts of our visible universe. They are currently speeding away from us at speeds nearing 3 times the speed of light. However, these galaxies do not move through space at relativistic speeds. Instead, expanding space propels distant galaxies forward like passengers on a cosmic escalator. The galaxies actually move at relatively slow rates in local space, but the cumulative effect of billions of light-years of expansion produces apparent recession velocities. That exceeds the speed of light. Hubble's law estimates cosmic expansion using a simple link between distance and recession velocity. Galaxies are twice as far away and disappear twice as fast. 3 times the distance equals 3 times the speed. This linear association persists until the recession. Velocity surpasses the speed of light at distances greater than 14 billion light-years. The finding of accelerated cosmic expansion earned the 2011 Nobel Prize in Physics. Observations of distant supernova indicated that expansion rates are increasing over time, rather than slowing as scientists predicted. This accelerated expansion against gravitational forces is driven by dark energy, which accounts for 68% of the universe's contents. Current growth rates indicate that space will double in size every 10 billion years. This may appear leisurely in comparison to human timelines, yet cosmic expansion occurs over such enormous distances that its effects compound to huge velocities on large scales. Because cosmic expansion is accelerating, the majority of galaxies we can see now will someday vanish beyond our cosmic horizon. In about 2 trillion years, only galaxies in our local group will be visible to future astronomers. Except for our galactic neighbors, the night sky will appear nearly barren nonetheless. Expansion rates may continue to rise until dark energy overwhelms all other forces in the universe. Theoretical models imply that accelerated expansion may eventually tear apart galaxies and star systems. Even atomic nuclei will be destroyed in an event known as the Big Rip, which occurs around 22 billion years from now. However, the current expansion rate provides opportunities as well as isolation space. Telescopes may study galaxies at distances where recession velocities approach light speed. These observations offer an insight into cosmic circumstances when the cosmos was young, and star creation rates surpassed present levels. The expanding universe also permits astronomers to see further back in time by observing more distant objects. Each increase in telescope sensitivity reveals an earlier cosmic period, yet expansion transports the majority of the cosmos beyond our reach.